Hi Kidlets, this is your Phases of the Moon video. This is section 3 of your notes because the first two were combined. This will also contain information that will greatly assist you with your moon observation. So phases of the moon are not caused by a reflection of the sun. They are not caused by a reflection of Earth. They're caused because as the moon rotates around us, we see the illuminated portion changing. So it's our perspective, it's our view that's changing. Because if we look at this inner circle of moons, we can see that they're all technically half moons, because the side that is always facing the sun is the side that is always lit. So it's really, if you were looking at an orbital view, it is always a half moon, but it's our perspective that changes. So we have, really, you can break this down into four major phases. We really have new moon. I'm going to cross these guys out. New moon, quarter moons, and full moon. So forget all of the rest of them for right now. So new moon is when you have the moon that is between the position of the Earth, so this guy is the Earth, and the sun. So you can remember that because, remember, look at this inner picture here. You can see the side facing Earth is dark. And the noon means that it's at its highest point at noon. So then at a 90-degree angle to us, so perpendicular to the alignment of the sun and Earth, is the first quarter moon. And that would be at its highest point at sunset. So then opposite, but still in alignment with Earth and sun, so on the far side, is the full moon. So here we can see the side facing us is illuminated. And remember that always half is illuminated. It's just our perspective. And then last quarter, sometimes called first quarter. So if you look at your quarter moon phases, you can see that from Earth's perspective, last quarter has the left side illuminated, and the first quarter has the right side illuminated. Notice from the orbital view, it's always the sunward side. But again, it's our perspective. So now the way we can remember our crescents and our gibbuses is because everything waxes on the way to full, and it wanes on the way to new. So crescents, when we see just this teeny sliver of illumination, is surrounding our new. It means almost new. It's either just after or just before. Gibbous, and you're all going to ask what the heck gibbous means. I had to look it up. In, I believe it's Greek, it means plate, and in Latin it's humpback. Humpback. What that has to do with the moon, I have no idea, but that's what it is. So again, waxes on the way to full, it wanes on the way to new. So surrounding our full moon are our gibbuses. So it's waxing as it's getting bigger, it's waning as it's getting smaller. So if you've seen Karate Kid, yes, I've dated myself, wax on, wax off. So the illuminated portion is growing on the way to full, the illuminated portion is shrinking on the way to new. And you can see that the times that the moon is at the highest, it is always about a 6-hour difference. So this would be like a full cycle. So new moon is the highest at noon, first quarter highest at sunset, full moon highest at midnight, last quarter highest at sunrise. And this would also be a way that you could draw your sun, moon, earth geometry for your observation. What I mean by that is, where is the position of the sun, where is the earth, and for that given phase, where is the moon around it? So here you see all 8 orbital phases. So you are going to be observing from this phase to this phase. So you would just draw where in that is the earth, where is the moon. So where is that alignment? So you can see the full moon, it's perfectly in alignment, your quarters are perpendicular, and all of your phases are going to be somewhere between that. That's what the sun, moon, earth geometry is. So here shows that in a bit more detail. So here you can see our new moon is, there's the earth, there's the moon, there's the sun. So this is that orbital geometry. That's what I mean. Here's a waning phase, there's your first quarter, there's a waxing gibbous, full, waning gibbous, last quarter, waning crescent, and here is just past the new phase again. And here you can see from our perspective what each of those moons would look like. And since each of these are in a different position around Earth, that means that the time of moonrise is changing every single night. This is why you're observing for 2 weeks at the same time exactly every night, so you can see where in the sky is the moon for your given time of the month. And one reason that we see the same side of the moon all the time is because it is synchronously rotating. That means that it is rotating the same. And what is the same is the rotation and the revolution. So because we are larger than the Earth, we have slowed the moon's rotation to where its rotation, and remember rotation is equivalent to a day. Oh, that's really big. And revolution is equivalent to a year. So that means that the time it takes for the moon to get back to this place is the same time that it has done a complete rotation on its axis. So that would mean that that's why we see the same side of the moon all the time. It is very slowly rotating all the way around the Earth. So here we can see our little dude, and the moon is just slightly rotating each day to get back there. So its day and its month are equivalent. And that's why we see the same side. It's not because it doesn't rotate, it's because it does. And the moon is having the same gravitational effect on Earth. Our rotation is slowly changing. It is slowly slowing down. So our days are getting longer. And we'll see that in a second when we talk about tides. So here again are our different phases. And the phases again are caused by our perspective of the changing moon as it's rotating around us. And here again we can see, let's go with our lightsaber this time. Here again we can see that the orbital view is always half. But our geometry, our sun, moon, earth geometry is what changes. And as a result of that geometry, where it is in location around us in relation to the sun, that's why we see those phases. And here is showing the whole progression of what we would see of the moon all the way through. So from waxing to first quarter to waning to last quarter to your crescents again. So, and the thing to note is how your waxing phases appear different than your waning phases. That's how you can tell. That and the time of day or night they're up. So waxing is always going to appear to be illuminated on the right side. Your waning is always going to appear, look at your little dude, and from his perspective, this is left. So because the moon is changing its position around us from day to day throughout the course of a month, that means that the time of moonrise also changes. So we would see all of our waxing phases generally in the early morning because the full moon rises at sunset and sets at sunrise. The new moon then rises at sunrise, sets at sunset. So this would be the progression of all of our waxing phases. So at sunset, here would be, if you're looking at sunset, each of these different positions, that would be when you would see them. So it would appear that the moon is moving from right to left or west to east. In the same way then, our waning phases would be seen in the morning sky. And the moon rises nearly an hour later every single night. It's actually about 52 minutes that the moon rises later. So that gives us nearly a month. But a month, as we know it as, is not exactly a month. So we talked in the last unit about sidereal motion and synodic motion. We talked about that briefly in a solar day and a sidereal day. And even though during a day it only has the consequence of 4 minutes, in terms of a month and the moon moving around us, not just our rotational axis, we have a difference of about 2.3 days. So it is significant. So as a reminder, remember that our sidereal period is just the time it takes for the moon or whatever object it is to just do a full 360. So if we look here at position A, we can see that we're starting at a new moon. So our geometry is perfectly aligned. So we have a parallel line from Earth to moon to sun. So that's our sun, moon, earth geometry. So then we move to position B. Once the moon has done a complete 360 rotation around us, because Earth has also moved along in its orbit, Earth is not staying in the same spot. A month later, once the moon has done a full 360, Earth is now here. So because Earth is now here, now after that full 360 motion, it's not realigned with the sun. So it has to then rotate. So here we can see the star, but it's not realigned with the sun. So it has to continue to move in its orbit for 2.2 days in order to realign with the sun. So that sidereal period is the time it takes for it to do a full 360 motion. Remember sidereal, the real rotation, so that's 360. Whereas our synodic period is phase to phase, full moon to full moon, or new moon to new moon. So that's when it has to continue to move along in its orbit in order to realign with the sun. So the time it takes to get back here, or to get back to a full moon, which would be here, there, and here in this position, where it's perfectly in a line. So here is just showing that again. If you are looking at the PowerPoint version of this and you're in present mode, you will see a pretty cool little animation here that really shows that. So again, here would be our new moon position, and the moon is rotating around Earth, but Earth is also rotating around the sun. So in this position, it's already done a full 360, but it's not in the same spot to give us the same phase. So you will need to know what the actual periods of each are and what the difference in each is. So if I were to give you a picture, this would be how you would label it. And again, this is our sun, moon, earth geometry. So here is the geometry of a new moon, perfectly in alignment. But then after the earth has moved along in its orbit and the moon has done a full 360, it has to continue to rotate just over 2 days in order to realign with the sun. So you will need to know the length of each of these. So the last section is about tides. Tides are a gravitational consequence of the alignment of the earth, sun, and moon. And tides is that pull on the water because of that gravitational tugs of the sun and the moon. It's actually due to each, not just one of them. So they can align perfectly, and the pull will drag the water. It also drags the rock. They've done studies to show whether there are a greater number of earthquakes during new moon and full moon when you have this tug towards the moon and towards the sun on the backside. And I believe they've been inconclusive, but it does make sense. It's just easier to pull on water because it's less dense than rock. So we have two types of tides. We have spring tides and we have neap tides. Spring tides happen during our new and our full moon. And this is when the gravitational effects of the sun and the moon add up and it pulls on the water. And if you were to look at just a side profile of Earth at that time, it would make the Earth actually egg-shaped. Neap tides, also known as no tide, happen when the moon is in this position. So your quarter moons. So here and here. So here the gravitational effects of the moon and the sun cancel out. So when it's a quarter moon or a quarter moon, you have the cancellation of their gravitational effects. So you have the low tides. So tides happen twice a day. You have high tide twice a day. You have low tide twice a day. But when you have spring tides, which has nothing to do with the season, each of these happen twice a month. So spring tides happen at new and full. Neap tides happen at your quarter moons. So they each happen twice a day. So when the sun comes up, when the sun goes down. Or I'm sorry, when the moon is up and when the moon is down. It's aligned with the moon phase, not with the solar phase. So high tide or spring tides would bring us the highest highs and the lowest lows. Neap tides would be very neutral. You can think about neap as being neutral. And we also have this concept of tidal locking. And that's what's responsible for the synchronous rotation of the moon, or the rotation and the revolution being equivalent. And that is a result of tidal locking. The moon is tidally locked to the gravitational force of the Earth. So that has then slowed its rotation to where it's equivalent to its period of revolution. Wow, there is a box in the way here. So the tidal locking or coupling has also had an effect on the moon's interior. So Earth's gravitation has actually altered the interior structure of the moon to where the core is offset. We have this thicker far side. It's not called the dark side because half the time it's illuminated. We just can't see it. And the near side is very thin. Now, very recent studies like 2015 and 2016 have shown that the models of lunar formation are actually responsible for this thickening of the backside, and that there may have been initially a smaller moon which slowly was drawn into the larger moon and pancaked into it. And that would be why there's the thicker crust here. But that thinning of the near side crust is also responsible for more mare on our side. Because you just have a thinner crust, it's easier for that volcanic magmatic mantle material to come through. So we have this offset of the lunar interior. So there's no water on the moon, so the tidal forces have altered the internal structure. So here we can see that again, this direction towards Earth. Here we can see the crust, the mantle, the core, and it's all slightly offset to give us a thinner near side and a thicker far side. So here we can see just an animation and the Earth and Sun geometry of spring tides versus neap tides. So here we can see spring tides are our full moon and our new moon, and we can see this bulging on the moon side, and it would also be on the far side. And that's because the moon is also pulling on the Earth's rock. So in the slightest variation, it is actually altering the position of the Earth in its orbit and leaving behind this gap of water. So it's not just pulling on that near side. It's actually the far side has a tidal bulge as well. And then at the quarter moons, this perpendicular alignment cancels out any of the tidal forces. So we have very neutral, low, very medium highs, very medium lows, whereas spring tides would bring us the highest highs and lowest lows. Again, in the PowerPoint version, you can click play on this, and this will show a nice little animation of the moon going through each of the phases and the response of the tides. So the moon, even though it is smaller than the sun, has a larger gravitational influence over Earth's water than the sun does. And the reason why is the moon is much closer to us. Even though the sun is much larger, the moon has a greater gravitational force due to its distance. So the moon and the sun are both responsible, but to a greater effect, the moon is just due to its proximity. And if you are actually interested in the why of that, if you don't want to take my word for it, again, this is an asterisk item, so I wouldn't ask you these numbers, but if you actually wanted the meat of it as to why the moon has a greater force, that comes down to the proportionality. So if we take the mass of each body, so the tidal force proportion is equivalent to the mass divided by the radius cubed. So if we were to look at the math of that, if we took the mass of the moon divided by the radius of the moon cubed, we get a larger number, nearly 2 times greater than that proportion of the sun. So this is the why as to the force difference, why the moon has a greater effect than the sun does. That is it, guys. I will see you in class.